Hello guys, welcome to lecture 4 of our lecture series, Chemistry for Engineers. Today our topic will be on stoichiometry. So our objectives for today will be calculating relative atomic mass. I think we've looked at that before in our last lecture, as well as the relative abundance of each isotope, relative molecular mass, understanding the chemical composition of gasoline, which is basically simple. It's only hydrocarbons, understanding chemical equations for combustion to calculate products of chemical reactions, as well as reactants needed for product, understanding percentage yield of a chemical reaction, as well as additives in gasoline and their uses. Stoichiometry is referred to as a quantitative calculation for chemical reaction. So you're basically just dealing with numbers and calculation. Very important, a balanced chemical reaction is key to understanding any quantitative reaction. So when you balance a chemical equation, it actually provides mole ratios for all reactants and products. To use these ratios, we usually have to convert information from something such as mass, volume, or reactant. So in order to use these ratios, we usually have to convert information from something such as mass or volume or reactant or products to mole. This establishes the main pattern for solving stoichiometry problems. We usually convert from moles to mass or volume of the unknown substance. Another type of calculation that can be considered in stoichiometry problem is a percentage yield of a reaction. In this case, the amount of product determined in the problem presents the theoretical yield. So in terms of calculating the relative atomic mass is the average mass of one atom. The relative abundance of isotope is basically gaining an average of the total number of isotopes that exist and calculating an average. Say for example, carbon has 3 isotopes. Relative molecular mass of a molecule is the average mass of one molecule of a substance when compared to 1/12 of the mass of carbon. Chemical composition of gasoline, as we say, it's very simple. They're mostly hydrocarbons. So as we can see here, these are different examples of hydrocarbon: methane, ethane, propane, butane, the most common 4 hydrocarbons. Methane comprises of 1 carbon, 4 hydrogen. Ethane comprises 2 carbon, 6 hydrogen. Propane comprises 3 carbons, 8 hydrogen. Butane comprises 4 carbons, 10 hydrogen. Calculating the product of chemical reaction is very important, especially when you want to understand the percentage yield of a chemical reaction, and it also will assist in calculating the reactants needed for the product. It will also give an idea as to a quantitative value as to the reactant needed to produce a product. Gasoline additives can be alcohol such as methanol, ethanol, ethers such as methyl tetrabutyl ether, MTBE, tetraamyl methyl ethyl, TAME, or tertiary THEME. So as we mentioned before, stoichiometry refers to the relative relationship between the amounts of reactant and product in a chemical reaction. So it's basically giving a quantitative value of the product and reactants. So here we can see 2 hydrogen atoms react with 2 oxygen molecules to give you 2 water molecules. The relative atomic mass, as we've mentioned before, is basically the mass of a single atom divided by 1/12 of the mass of carbon. So for example, carbon dioxide molecule has a relative atomic mass of 44. In order to calculate the relative atomic mass, you'll have to know the atomic mass of carbon, which is 12, plus the atomic mass of 2 oxygen molecules. We know that the atomic mass of 1 oxygen is 16 grams, so 2 times 16 is 32. 32 plus 12 equals 44. So 1 mole of CO2, or 6.02 times 10 to the 23 molecules, has a mass of 44.01 grams. Isotopes are atoms of the same element that have different numbers of neutrons, as we mentioned before. Chlorine, for example, has 2 isotopes. It has an isotope with an atomic mass of 35 and an isotope with an atomic mass of 37. So the relative abundance of isotope 35 is 75%. The relative abundance of isotope of chlorine 37 is 25%. The relative atomic mass of an an element is the average value for the isotopes of the element. It takes in account the percentage of abundance of isotope. So it's basically saying that 75% of chlorine atoms exist as chlorine 35, while 25% exists as chlorine 37. So in order to calculate the relative atomic mass, 75% times 35 plus 25% times 37, which is the atomic mass, gives you 35.5. So the relative atomic mass of fluoride is 35.45. And here we can see this is just basically creating emphasis. So the relative atomic mass of chloride 35, this exists at 75% abundance. The relative atomic mass of chloride 37 is 36.966, which basically gives a percent of 24.20%. If you add the relative atomic mass times the percentage abundance of each, divide by 100, you basically get the percentage of relative atomic mass of chloride. The relative molecular mass of a compound is the mass of one molecule of that substance relative to the mass of carbon atom. All of these weight mass calculation is using carbon atom as a standard. We know that oxygen has an average atomic mass of 16, and oxygen basically comprises of 2 oxygen atoms. So that means that the relative atomic mass of 16 would be 16 times 2. The atomic mass of oxygen, which is 16.00 times 2, would give a molecular mass of 32 for one oxygen molecule. The relative molecular mass of CO2 is also easy to find if you understand that you would need to know the molecular weight or the molar mass of each atom. So for example, the relative molecular mass of carbon dioxide, which is CO2, you'll have to find the molar mass of carbon, which is 12, as well as the molar mass of oxygen, which we already know is 16. This would be 16 times 2 plus 12. That will give you 44. As we mentioned before, gasoline is a complex mixture, typically contain more than 100 different chemical compounds. The predominant compounds are hydrocarbons, which are molecules containing only carbon and hydrogen. Most of the hydrocarbon molecules in gasoline are alkanes. These are compounds whose carbons are linked together by a single bond. So these are a list of the alkanes that exist: methane, ethane, propane, butane, pentane, hexane, heptane, octane, nonane, decane. As you can see, the molecular formula basically shows that methane is CH4, 1 carbon 4, and as you can see, the carbon atoms will increase by a factor of 1 for each. So as you can see, this is 1 carbon, this is 2, this is 3, this is 4, pentane is 5, hexane is 6, while the hydrogen atoms will increase by a factor of 2. So this is 2, this is 4 hydrogen, 6 hydrogen, propane, 8 hydrogen, butane, 10 hydrogen, pentane, 12, hexane, 14, 16, 18, 20, 22. So most of the alkanes in gasoline contain 6 and 11 carbon atoms. The general formula for alkane is CnH2n plus 2, where n is an integer. This means that if the compound contains n carbon atoms, then it will contain 2 times n plus 2 more of hydrogen. If we have alkane with 3 carbon atoms, like for example propane, then this will contain C3 2 times n plus 2 more hydrogen atoms. In essence, this will contain, let me just write it here, C3H2n plus 2. So n equals 3 plus 2 times 3 plus 2. This gives us 8. So here we can see propane has 8 hydrogen atoms. For alkanes with 4 or more carbon atoms, there are actually multiple possible structures having the same formula. We call these isomers. So an isomer is 2 or more structures with the same chemical formula. 2 or more structures with the same chemical formula are called isomers. For C5H12, 3 possible isomers exist, and this is pentane. For pentane, 3 possible isomers exist. As the number of carbon in the chain increases, the number of possible isomers increases rapidly. For C10H22, 75 isomer is possible. So for decane, 75 isomers are possible. But as you can see, for methane, ethane, propane, there are no isomers. Butane, 2 isomers are possible. Pentane, Butane, 3 isomers are possible. Hexane, 5 isomers are possible. Heptane, 9 isomers possible. And octane, up to 18 isomers possible, and so on. Iso means equal, mers means part. Generally, you have two types of isomers. You have structural isomers and stereoisomers. Structural isomers have the same molecular formula, but different rearrangement of atoms. When gasoline is burned in an engine, all of these various compounds undergo combustion, simultaneously reacting with oxygen from the air. Octane, which is C8H18, if assumed complete combustion, equation should show octane and oxygen as reactant and carbon dioxide and water as product. So the important thing is, for any chemical reaction, for calculation of any quantitative value from, for example, the amount of product, carbon dioxide and water produced from a chemical reaction, we have to start by balancing the equation. In this case, you have to balance the equation. And as we mentioned in our last lecture, we balance our equation by adding what we call the stoichiometry coefficient. So here, in terms of balancing this equation, the coefficients are 2. So on the side of the reactant and on the side of the product, you'll have to balance the equation. Any chemistry question that asks how much of a particular substance will be consumed or formed in a chemical reaction is a stoichiometry problem. So once you're asking for a quantitative number or value, it's a stoichiometry problem. At the heart of every such stoichiometry problem, you'll always find a balance equation. So the first thing you have to do if you have a quantitative problem is to balance the equation. The stoichiometry coefficient that balances a chemical equation refers to the number of particles and not to mass. So here, the coefficients that you insert is referring to the number of particles and not mass. Masses and volumes of liquids are the quantities that are more likely to be measurable. To make quantitative calculations for a chemical reaction, we need to convert between measured value of a mass or volume and desired volume of a number of moles. So you have to convert between moles and mass to basically get a desired quantitative values such as gram. So here, we're basically looking at the side of the reactant and we're looking at the side of the product. We're looking at 2 nitrogen atoms. So nitrogen, hydrogen are diatomic molecules, so they always come in 2. So we look at 2 nitrogen plus 2 hydrogen. This basically gives a product of ammonia, which basically means that you end up with 1 nitrogen, 3 hydrogen. So on this side of the equation, you have 2 nitrogen, 2 hydrogen. On this side of the equation, you have 1 nitrogen and 3 hydrogen. When balancing a chemical equation, there should be an equal number of every atom on both sides. As you can see, this equation is unbalanced. So to balance this equation, what you can do, you can insert 2 here and you can insert 3 here. So we end up with 2 nitrogen on both sides. So this is 2 nitrogen, this is 2 here and 2 as well. And inserting this 3 basically gives you 6 hydrogen. So 3, 2, 6 here. And inserting this 2 basically gives you 2, 3, 6. And this is basically a balanced equation. So the 3 that was inserted here or here, the 2 that was inserted here is basically called the coefficient. The simplest combustible hydrocarbon and one of the simplest of all fuel is methane, CH4. So we can say that the equation shows 1 mole of methane reacts with 2 moles of oxygen to produce 1 mole of carbon dioxide and 2 moles of water. From the chemical equation, we can write the following mole ratio. So we have 1 methane to 2 oxygen molecule, 1 methane to 1 carbon dioxide, which is the product, 1 methane to 2 hydrogen molecule, which is also the product, 2 oxygen molecules to 2 hydrogen molecules. So this is the side of the reactant, 2 oxygen molecule to 2 hydrogen molecules. So if you analyze this in ratio, we have 1 methane to 2 oxygen molecules, we have 1 methane molecule to 1 carbon dioxide molecule, we have 1 methane to 2 hydrogen molecules, and we have 2 oxygen to 2 carbon dioxide, and it's also represented here. So 1 methane molecule plus 2 oxygen molecule gives you 1 carbon dioxide molecule in the form of gas and 2 hydrogen molecule in the form of gas. When doing stoichiometry calculation, mole ratios are very often written to look like fractions. They are used analogously to unit conversion factor relating the amount of one substance to that of another. another. So you basically write it like ratios. For example, methane, the 1 methane to the 2 oxygen, the 1 methane to the 1 carbon dioxide, 1 methane to 2 hydrogen, 2 water molecule, 2 oxygen to 2 hydrogen. So you basically write it in mole ratios. So methane plus oxygen gives you carbon dioxide and water. And to balance the equation here, they inserted 2 on this side, a coefficient of 2 on this side, to basically have both sides to have the same atoms. Because from our last lecture, we'll remember that in a chemical reaction, the law of conservation states that matter cannot be created or destroyed. It basically changes in a different form. If you start the reaction with 5 atoms, 10 atoms, you should end up with the same amount on the side of the product. So let's look at a problem. In the combustion of methane, how many moles of oxygen are required if 6.75 mole of methane is to be completely consumed? So the first thing you have to do when you get a problem is to balance the equation. So methane's reacting with oxygen. If we have 6.5 moles of methane reacting with oxygen to produce carbon dioxide and water, how many moles of oxygen is required? So here we have methane, 2 oxygen molecules to give you carbon dioxide gas and water, right? The coefficient from this equation gives us the ratio between methane and oxygen, which can be expressed in either of the following form. As we say, you can write it the same way: 1 mole of methane to 1 mole of oxygen, or 2 mole of oxygen to 1. So the ratio is a 1 in 2 or 2 in 1. To calculate the desired amount of oxygen from the known amount of methane, we should use the second form. This gives us the result: 6.75 mole of methane times 2 mole of oxygen divided by 1 mole of methane is 13.5 mole of oxygen. So you'll also find that some things are given in grams, so you have to convert or calculate, because to carry out the reaction in a laboratory, you often have to use a balance to measure out the material needed, and you usually don't do this in mass, you do it in grams. So we need to be able to convert between grams and moles. You have to use the Avogadro's number as a conversion factor. And remember that we said 1 mole of an atom is 6.02 times 10 to the 23 particles. 1 mole of a particle is 6.02 times 10 to the 23 particles. So anytime you get a question or equation or a solution, something to solve, and it's asking you for the number of atoms, molecules, formula units, ions, you basically have to refer to the Avogadro's constant. So 1 mole of iron, for example, would be 1 divided by 6.03 times 10 to the 23. So you have to convert the moles to mass. So how do you get this 55 grams? You basically have to look at the atomic weight of iron and divide this by 1 mole. 1 mole of iron is 55.8 grams. This is basically reflecting the atomic weight. We can see that if we begin with the mass of one species in the reaction and we want to know the mass of some other species consumed or product, we have to use 3 ratios. So if you want the mass of one species, you have to convert using 3 ratios. First thing is you have to find the molar mass of a given element and the molar ratio from a balance equation. Then you have to balance the equation and get the molar mass of that balanced equation and the ratio using the molar mass of the substance whose mass you wish to find. So you get the molar mass of the element, balance the equation, and then you get the molar mass of whatever you're trying to find. The simplest and most reliable way to identify which ratio to use for each step is to write all quantities with their complete units attached. How many grams of water can be produced if sufficient hydrogen reacts with 26 grams of oxygen? How many grams of water? So you're trying to find out how many grams of H2O you can produce if sufficient hydrogen react with 26 grams of oxygen. So recall that both hydrogen and oxygen are diatomic gases. So the balance equation is this: 2 hydrogen in the form of gas plus 1 oxygen molecule gives you 2 H2O in the form of gas. So in order to basically find out how many grams of water you need, so you have to find the mass of 26 grams of oxygen, the mass that is given, the molar mass ratio of oxygen. So you have to find the molar mass of oxygen. So oxygen molar mass is 16. So this would be 16 times 2, that gives you 32. The mole ratio between the equation now would be 2 mole of water, that will give you 1 oxygen molecule. So you times this, 18 grams of H2O. So the 18 basically means that there is 2 hydrogen. Remember that hydrogen has an atomic mass of 1.01. So this is 1.01 times 2, that would give you 2. Oxygen is 16, so 16 plus 2 will give you 18 grams of H2O. Divide by 1 mole of H2O, and that basically gives you 29.3 grams per H2O. In terms of calculating between gallons and mass, now we can relate the amount of carbon dioxide emitted by an automobile engine and the amount of gasoline burned. What mass of CO2 will be produced for every gallon of gasoline used? Starting by assuming that our simple model using the complete combustion of octane to represent the burning of gasoline. So we're going to use octane as the gasoline. The balance equation is this. So we have 2 octane plus 25 oxygen molecule gives you 16 carbon dioxide plus 18 H2O. Here, this is basically just inserted here, even though it's actually talking about theoretical yield, and we'll get there eventually. First, you'll have to find the mass of octane. So find the mass of 8 carbon. So carbon 8. So we know that carbon has an atomic mass of 12. So that would be 12 times 8. Plus, we know hydrogen. What is hydrogen? Hydrogen is 1.01. So that would be 1.01 times 18, which basically gives you 18. So 12 times 8 plus 18 gives you 114.23. And here you'll have to find the mass of oxygen, which you already know. The mass of oxygen is 16, so this would be 16 times 2. So that basically gives you 32 grams per mole. The mass of H2O, you already know, as we mentioned before, hydrogen is 1, so that's 1 times 2, plus oxygen, you know, is 16, and that basically gives you 18. First, you have to start by balancing the equation, then calculating the mass of each molecule. Because we are basing our calculation on octane, it might be reasonable to use the density of octane, which is 0.725 grams per mil. We convert into gallon, so we basically will have to convert the density to mils because we're dealing with volume. The conversion factor to find mass, you're trying to find the mass in grams of a gallon of octane. So this is the 1 gallon of octane. You're trying to find the mass. So if you convert a liter to gallon, a 1 gallon in the form of liter is 3.78. That would be times 1000 mils. So divide by 1 liter times the density of octane, which is 0.725 gram. This basically gives you 2659. So this is basically in grams in 1 gallon of octane. So now we are trying to find what mass of CO2. So what's the mass of CO2 that is produced by a complete combustion of 2659 grams of octane? So 2659 grams of octane, you're trying to find out the mass of CO2. So you use the molar mass and the mole ratio from the balance equation to set up the calculation. So 2659 grams of octane times 1 mole. So 1 mole of octane, and as we did before, we know that 1 mole of octane is equivalent to 114.23 as we've calculated with the carbon as well as the hydrogen. Remember that we said that this would be 12 times 8 plus 18. That would give you 114. You times this by 16 mole of CO2 divided by 2 octane. You basically will have to find the mass of CO2 or atomic mass of CO2, which would be 44 grams, and divide that by 1 mole of CO2. You basically get 8,196 grams of CO2. So to basically put this in familiar units, you use the fact that a pound is approximately 454 grams. So if you divide the 8,000 by 196 grams, you basically get 18 pounds of carbon dioxide that is produced from complete combustion of 2,659 grams of methane. When dealing with stoichiometry calculation, you'll also have to deal with what we call limiting reactants. When we carry out a chemical reaction, the available supply of one reactant is often exhausted before the other reactant. So you're combining 2 reactants reactants together to give you a product, usually one might become exhausted. So there's so much and no more combinations that you can have. If you run out of one reactant, the reactant basically stops, because the reactant will need the other reactant to combine to give you the product. Reactant completely consumed in the reaction is the limiting reactant. So whichever one that is completely consumed is the limiting reactant. This molecular scale picture illustrates a concept of limiting reactant. The box on the left represents the mixture of reactants in our hypothetical experiment. 6 hydrogen molecule and 6 oxygen molecule in red. So the hydrogen molecules are shown in white, oxygen molecules are shown in red. The right hand side shows the molecule present once the reaction has gone to completion. The 6 H2O molecules and 3 unreacted oxygen molecules. So basically we said that the 6 H2O molecules and 3 unreacted O2 molecules. Here H2 was the limiting reactant because no more hydrogen molecules are available to react with the unbound oxygen molecules. So remember that we said that 6 oxygen molecules, so the oxygen molecules are in red. So we have the oxygen molecules here that are in red with no hydrogen to react with them. And this means that the hydrogen are completely consumed at the end of the reaction. So this means that the hydrogen molecule is the limiting reactant. So remember that you need 2 hydrogen for 1 oxygen. So naturally, hydrogen is more likely to be consumed. Your car may run out of gas, but it may not run out of oxygen. What is more likely to be a limiting reactant? The limiting reactant is more likely to be the hydrocarbons, right? In any calculation related to fuel consumption or exhaust emission, it would be reasonable to assume that gasoline would always be the limiting reactant, because the gasoline is reacting to form the product of oxygen. Oxygen is abundant and is highly available. So balanced chemical equation tells us the ratio in moles of one substance react with moles of another. So this is basically just looking at a limiting reactant. Here is the reactor that is completely consumed, as we know before, using the mole ratio in a balance equation. So you can find this using the mole ratio using a balance equation as well. So for example, iron plus sulfate basically gives you ferrous sulfate or iron sulfide. So here we can see the limiting reactant is sulfate and the excess reactant is iron. So because we have more iron that needs to react with sulfate. A solution of hydrochloric acid contains 5.22 grams of hydrochloric acid. When it is allowed to react with 3.2 grams of solid potassium carbonate, K2CO3, the products are potassium chloride, CO2, H2O. The products are KCl, CO2, H2O. Which reactant is in excess? So this is basically the skeleton of the equation. So hydrochloric acid plus potassium carbonate gives you potassium chloride plus carbon dioxide plus water. The first thing you need to do is to balance the equation. So with a balanced equation, we'll have 2 HCl plus K2CO3, which gives you a product of 2 KCl plus CO2 plus H2O. Quantity of HCl given and calculate the amount of KCO3 that would react completely with it. So basically, we're looking for a solution of hydrochloric acid that contains 22 grams of hydrochloric acid. So if you allow this to react with 3.25 grams of solid K2CO3, the products are these, which we're looking for the reactant in excess. Finding the reactant excess, we automatically will find the limiting reactant as well. 5.22 gram of HCl times 1 mole of HCl. So you'll have to find 1 mole, the equivalent of 1 mole in gram of HCl. So the 1 mole of HCl would be equivalent to 36, because we have hydrogen times 1, so that would be 1. We have chloride times 1, so 1 chloride is 35 plus 1 mole, that would basically give you 36.4 times 1 mole of potassium carbonate divided by 2 mole of HCl. Remember, we're looking at the ratio. 1 mole of this is basically reacting with 2 moles of this. So 1 mole of this is reacting with 2 moles of this. So 1 mole of KCO3 divided by 2 mole times 1 mole of CO3 KCO3 is equivalent to 138 grams of K2CO3. Naturally, we get this by finding the atomic weight of potassium, oxygen, and divide this by 1 mole of KCO3. So you basically end up with 9 grams of KCO3. So the given quantity of KCl, which is 5 grams, requires 9.8 grams of KCO3, but we only have 3.2 grams of KCO3 available. So the reaction will stop once the KCO3 is consumed. KCO3 is a limiting reactant and hydrochloric acid is in excess. So basically 5.22 grams requires 9.89 grams of KCO3, and you basically only have 3.2 grams of KCO3 available. So KCO3 is the limiting reactant. We're short on KCO3. So here, this is basically showing the representation of iron and sulfate as we discussed previously. And as you can see, the sulfates are represented by the yellow atoms. Iron is represented by the red atoms. In this case, we see that iron is the limiting reactant because we have unbound sulfate here. Ammonia is widely used in the production of fertilizers and is also a precursor to a number of important polymers. So the formation of ammonia from its element is one of the most important industrial chemical reactions. N2 plus 3 H2, so 2 nitrogen plus 3 times hydrogen will basically gives you ammonia. How many grams of ammonia can be made from 3.50 grams of H2 gas and 18.0 grams of nitrogen gas? What is left? We first have to balance the equation. So we have N2 plus 3H2 gas, which basically gives you 2NH. So you want to check if this equation is balanced? Sure. So we have 3, 2, 6, 3 hydrogen here, 3, 2, 6, 3 hydrogen. We have 2 nitrogen. We have 2 nitrogen here. So you're given the grams of hydrogen. So 3.50 grams of hydrogen. So the ratio is 1 mole of H2 divided by 2H2, 1 mole of N2 divided by 3H2. Hydrogen. So first you have to find the atomic mass of nitrogen, which is 14. So this is 14 times 2, which gives you 28. You also have to find the atomic mass of hydrogen, which is 1, which basically gives you 16.3 grams of N2. So H2 basically ends up being the limiting reactant and N2 becomes the excess reactant. So we're looking at the amount of ammonia that can be made from the combination of hydrogen and nitrogen gas. If you have 3.5 hydrogen gas and 18 grams of nitrogen gas, what's left? We basically have 16.3 grams of nitrogen. So what's left is 16.3 grams of nitrogen. In that case, nitrogen is the excess reactant. The reaction that produces tetraphosphorus trisulfide, one of the reaction in the combustion of a match, is 8P4 plus 3S8, which basically gives you 8P4S3. If 28 grams of P4 is allowed to react with 18 grams of S8, which is the limiting reactant. So it's the same thing again. You get 28 grams of P4. You basically find 1 mole of what P4 is equivalent to in terms of mass. Atomic weight of phosphorus is 30 and we have 4. So this would be 30.9 times 4. That basically gives you 123 grams. This times 3 mole of S8, 32.05 times 8 is 256. You divide this by the 8, which is the P4. The 256 divided by 1 mole of S8. This basically gives you 21 grams of S8. 28.2 grams of P4 requires 21 grams of S8 to react completely. We have only 18 grams of S8. So there is not enough S8 to react with all the P4. Therefore, S8 is the limiting reactant. So we have 28 grams of P4, which requires 21.9 grams of S8 to react completely. stoichiometry. Remember, we have 18. So we have only 18 of S8. So there is not enough S8. So we don't have enough S8. We only have 18, but we require 21.9. Therefore, S8 is the limiting reactant. MTBE, which is methyl tet-butyl ether, has been used as an additive in gasoline, and we'll see that in the end. The compound is produced by reacting methanol and isobutene according to the following equation. So you have CH3OH, methanol, with isobutene, which basically gives you MTBE. So MTBE is basically produced by methanol and isobutene. If 45 kilograms of methanol is allowed to react with 70 kilograms of isobutene, what is the maximum mass of methyl tet-butyl ether, MTBE, that can be obtained? So basically we have to start by balancing the equation. As we already know, we'll need the molar mass for all three compounds as well, taking care to interpret the parentheses. The molar mass of methanol would be 32.042. The molar mass of isobutene would be 56.10. So we know that carbon is 12, so that would be 2 times 12. Hydrogen is 1, so we have 2 3 is 6. And we also have 1 carbon, another carbon, and 2 hydrogen. That basically gives us 56. MTBE is CH3, and the parentheses is added again, which means that this is 3 carbon and 3 threes, and this would be 9 here, and we end up with a molar mass of 88. So the molar mass of methanol is known, isobutane is known, and MTBE is also known. So let's get to the calculation. So we have 45 grams of methanol allowed to react with 70 kilograms of isobutene, and we want to know the maximum mass of methyl tetrabutane, or MTBE, can be obtained. To identify the limiting reactant, we can calculate the mass of isobutane with 45 kilograms or 45,000 grams of methanol. This could be 45 kilograms or 45,000 grams of methanol. Here we have to do the ratio as well. So we already know that 1 mole of methanol is 32 grams. We know that 1 mole of isobutane is 56.17 grams. So this basically gives us 7.88 times 10 to the 4 isobutane, which basically gives us 78.8 kilograms of isobutane. This tells us that to use 45 kilograms of methanol, or 4,500 grams of methanol, we need 78 kilograms of isobutane. But we only have 70 kilograms of isobutane. So the amount of isobutane available will be determined by the amount of MTBE that can be formed. Isobutane is a limiting reactant and methanol is in excess because we need 78.8 kilograms of isobutane and we only have 70. Now the problem is reduced to a simpler stoichiometry calculation starting from the mass of isobutane available. So 70,000 grams of isobutane, or 70 kilograms of isobutane, times 1 mole of isobutane, which is 56.107, times 1 mole of MTBE, which is 88.19, basically gives us 1.103 times 10 to the 2 kilograms of MTBE. The solid fuel booster rocket of space shuttle are based on the following reaction between ammonium perchlorate and ammonia. So we have ammonium perchlorate and aluminum, giving you aluminum oxide, aluminum chloride, iron nitrate, and water. If either reactant is in excess, unnecessary mass will be added to the shuttle, so a stoichiometric mixture is desired. So you don't want anything to be in excess. What mass of each reactant should be used for every kilogram of fuel mixture? We want to ensure that there will be no excess of either reactant because we are asked for the composition of every kilogram. We might start by assuming that the total mass of fuel will be 1,000 grams. So we can write it as this: the mass of ammonium perchlorate plus the mass of aluminum is equal to 1,000 grams. The mass of ammonium perchlorate plus the mass of aluminum is equal to 1,000 grams. Because we have two unknowns, we will need a second relationship between the two masses. The balanced chemical equation shows us that the mole ratio between two reactants should be 3:3 or 1:1. So when you balance the equation, it shows that it's a ratio of 3:3 or 1:1, whichever whichever, right? So the 3 would automatically also be equivalent to the 1. We can use molar masses to convert that to a ratio in terms of masses, and then use a ratio as a second equation to solve the problem. The molar mass of ammonium perchlorate is 117.49 grams, and so you basically get the molar mass by calculating 1 nitrogen, 4 hydrogen, 1 chloride, and 4 oxygen atoms. You basically get 117.49 grams per mole, and that of aluminum is 26, as we can see here. To ensure that we have a stoichiometric mixture, we need equal molar amount of each reactant. So if we were to use 117.49 grams per 1 mole of ammonium perchlorate, we need 26.9 grams. We also need the same mole of aluminum. So we can write it like this. So if you divide the 117.49 grams, which is the molar mass of sodium perchlorate, by aluminum, you basically get 4.355. And although our actual amount will need to be bigger than those, the ratio of masses will still be right. So now we have 2 equations for 2 unknown masses, and we can only solve by doing a little bit of algebra. Our 2 equations are, we have the mass of ammonium perchlorate plus aluminum, which we want both of them to be equivalent to 1000 grams. The mass of ammonium perchlorate is equal to 4.355 mass of aluminum. So substituting the right hand side of the second equation in the first equation gives 4.355. 4.355 mass of aluminum plus mass of aluminum is 1000 grams. Simplifying that and solving, we get the mass of aluminum needed for each kilogram of fuel. 5.355 mass of aluminum is equal to 1000 grams. You divide the 5.355 by 1000, you get 186 grams of aluminum. Now the mass of sodium perchlorate is easy to obtain because you already have the mass of aluminum. So if you have the mass of aluminum, all you now need to do is to minus the amount from the total grams, which is 1000. So you end up with 813.2 grams. So each kilogram of fuel should comprise 186 grams of aluminum and 813.2 grams of sodium perchlorate. Next important calculation is percentage yield. We can rate the efficacy of a reaction by calculating how much product would form under perfect or ideal conditions, and then comparing the actual measured result with the ideal. So the ideal amount of product is called the theoretical yield. The ideal amount of product that you would want is the theoretical yield, and it is obtained by working a stoichiometry problem. Measuring the amount of products formed gives us the actual yield. So if you measure the amount of products that is formed, that's the actual yield. From the ratio of actual yield and the theoretical yield, we can calculate the percentage yield. So the percentage yield is the actual yield divided by the theoretical yield times 100%. When 45.8 grams of potassium carbonate reacts with excess hydrochloric acid, 46.3 grams of potassium chloride are formed. Calculate the theoretical and the percentage yield of potassium chloride. So the actual yield is 46.3. To find the percentage yield, you'll have to divide the actual yield by the theoretical yield and times that by 100%, which basically gives you the percentage yield. Increasing this percentage yield is one of the foremost goals of the chemical engineers working on an industrial process. The Salve process is important in commercial production of sodium carbonate, which is used in manufacturing of glass. When 45 grams of potassium carbonate reacts with excess hydrochloric acid, 46.3 grams of potassium chloride are formed. So how do we calculate the theoretical yield? We basically use the 45.8 grams of potassium carbonate, and we convert what 1 mole of potassium carbonate is, which is 138 grams. We also convert 2 moles because we get 2 moles of potassium chloride. 2 moles of potassium chloride divided by 1 mole of potassium carbonate. Each mole of potassium chloride is 74.5 grams of KCl. So this would basically be 45.8 grams divided by 1 mole of KCl CO3 divided by the actual mass in grams, divide by 2 moles of KCl, divide by 1 mole of KCO3. So 1 mole is 74.5 grams of KCl, divide by 1 mole. So you basically get a theoretical yield of 49.4 KCl. So the actual yield is 46.3 and the theoretical yield is 49.4 times 100, which basically gives you 93.7%. So here we can see we have an excess of hydrochloric acid. So the last step in the process is the conversion of sodium bicarbonate or baking soda to sodium carbonate by heating. So we have 2 NaCO3 in the form of a solid. You heat this, you basically get Na, sodium carbonate, plus CO2 and water. In a laboratory experiment, a student heats 42 grams of sodium bicarbonate and determines that 22.3 grams of sodium carbonate is formed. What is the percentage yield of this reaction? So again, to calculate the percentage yield, we need to find the theoretical yield. So you need to find the theoretical yield because you already have the actual, right? So we already have the actual yield, which is 22.3. To find the percentage yield, you'll have to find the theoretical yield. So we can do this by calculating the maximum quantity of the product that can be formed based on stoichiometry of the reaction. We have both the theoretical yield and the actual yield. Finding the percentage yield is straightforward because it basically dividing the actual yield by the theoretical yield. The 42 grams of sodium bicarbonate is equivalent to 84 grams per mole. The product, which is sodium carbonate, is 106 grams per mole. This basically gives us 26.5 sodium carbonate. So this is basically 26.5 grams sodium carbonate theoretical yield. So the actual yield, which we already know was 22.3 grams, divided by the 26.5, basically gives us a percentage yield of 84.2%. And remember, we refer to the atomic mass of sodium, which is 22.9, hydrogen, which is 1, carbon, which is 12, oxygen, which is 16, to basically give us the total mass in grams. And here we have the actual calculated mass of the sodium bicarbonate. So we have 23 or 22.99, which is the sodium. We have the 1, which is the hydrogen. We have the carbon, which is 12. And we have the oxygen, the 3 oxygen, which is basically 16 times 3. That basically gives you 84. And if we should look at the mass for Na2CO3, this would also be 23 times 2 plus 1 carbon, which is 12, plus 16 times 3, and that basically gives us 106.0 grams. Solution stoichiometry deals with the conversion of chemical reactions in volume. Basically deals with volume and concentration. So the number would be equal to mass times volume. So you basically have to balance the equation in moles and desired volume per mole. The fuel hydrazine can be produced by the reaction of solution of sodium hydrochloride and ammonia. The relevant chemical equation is here, where you have sodium hydrochloride in aqueous solution, which basically reacts with ammonia to give you hydrazine plus sodium chloride and water. If 750 mils of 0.806 mole of sodium hydrochloride is mixed with excess ammonia, how many moles of hydrazine can be formed? If the final volume of the resulting solution is 1.25 liter, what will be the molarity of hydrazine? Because ammonia is said to be in excess, we know that sodium hydrochloride will be the limiting reactant. So we will use the given volume and concentration to find the number of mole of sodium hydrochloride reacting. Then use the mole ratio for the balance equation to find the number of mole of sodium hydrochloride that can be formed. We can use the number of moles and the given final volume to obtain the molarity. So you convert 750 mils to 0.75 liter and determine the number of mole of sodium hydrochloride reacting. So the number of sodium hydrochloride is the moles times volume, equivalent to 0.806 per liter times 0.750 liter water, that is equivalent to 0.65 mole of sodium hydrochloride. Use that along with a 1:1 ratio of a balance equation to find the corresponding number of mole, 0.65 mole of hydrochloride times 1 mole of the same of hydrazine. So basically 1 mole of hydrazine divided by 1 mole of sodium hydrochloride is 0.605 mole of hydrazine, N2H4. To answer the second part of the problem, we just need to use the number of moles along with the given final volume to find the molarity. So the mole is basically the number over the volume. So the 0.65 mole of hydrazine divided by 1.25 liter gives you 0.484 mole per hydrazine. Notice the stoichiometry calculation is done using mole ratio from balance equation. Only the conversions to and from numbers of moles have changed because the reaction is in solution. You basically do this because the reaction is in solution. A common laboratory technique called titration requires understanding solution stoichiometry. A solution phase reaction is carried out under control conditions so the amount of one reactant can be determined with high precision. A carefully measured quantity of one reactant is placed in a beaker or flask. A dye called indicator can be added to the solution. The second reactant is added in a controlled fashion, typically by using a burette. When the reaction is complete, the indicator changes color. When the indicator first changes color, we have a stoichiometric mixture of reactants. So this is basically before the reaction, this is after the reaction, and in this case, you basically should have a color change. The photo sequence shows some of the steps in the typical titration. One solution is poured in a burette in the left-hand panel. The second solution is placed in the flask, and the burette is positioned above the flask in the second panel. The value on the burette allows controlled addition of solution, and the shape of the Eldenmeyer flask permits easy mixing and swirling in the final panel. The solution in the flask turns pink when the endpoint is reached. Many common titration involve the reaction of an acid with a base. If 24.75 ml of 0.503 mole of sodium hydroxide solution is used to titrate 15.0 ml sample of sulfuric acid, which is H2SO4, what is the concentration of the acid? So a titration problem is an applied stoichiometry problem, so we will need a balanced chemical equation. We know the molarity and the volume of NaOH solution, so we can find the number of moles reacting. The mole ratio from the balance equation let us calculate moles of hydrogen sulfide or H2SO4. The mole ratio from the balance equation let us calculate moles of sulfuric acid from moles of sodium hydroxide. So because we know the volume of the original sulfuric acid solution, we can find its molarity. The acid-base reaction will produce sodium sulfate and water. The balance equation is here, H2SO4 in aqueous solution plus 2NOH in aqueous solution. That basically gives us sodium sulfate and water, or Na2SO4 and water. Determine the number of mole of NaOH from the given molarity and volume. To determine the mole of sodium hydroxide from the given molarity and volume, so 0.02475 liter solution from a 0.045, so you basically convert that into liter. You divide the 0.53 mole of NaOH by a liter, and that basically gives you 0.012 mole of sodium hydroxide. Use the balanced chemical equation to determine the number of moles of hydrogen sulfide, 0.012 mole of sodium hydroxide times 1 mole of hydrogen sulfide divided by 2 moles of sodium hydroxide basically gives you 6.22 times 10 to the minus 3 mole of hydrogen sulfide. Determine the concentration of hydrogen sulfide or H2SO4, 6.22 times 10 to the negative 23 mole of H2SO4 or hydrogen sulfate or sulfide divided by the solution in volume, which is 0.01500. This basically gives you 0.41 mole of hydrogen sulfide. Gasoline you buy is also likely to contain fuel additives. Specific reason for using these additives generally fall under 3 broad categories: to improve engine performance, to reduce undesirable engine emission, to reduce dependence on import and petroleum products. Some additives can be achieved achieve more than one of these goals simultaneously. In the gasoline industry, the different grades of fuel are usually described in terms of their octane ratings. Higher octane numbers are expected to deliver better engine performance. Octane number is really a measure of how highly the gas can be compressed in the engine cylinders before it will spontaneously ignite. This allows an engine to operate at higher compression without unwanted knocking, which occurs if the fuel mixture in a cylinder ignites prematurely. The term octane number has its origin in the fact that octane itself is highly compressible. One way to achieve a higher octane number is to increase the fraction of octane in a particular gasoline. What is important is that the compressibility of gas, not the amount of octane present. So you have different types of additives, oxygenates, antioxidants, anti-NOx agent, fuel dyes. There are a number of ways to improve compressibility that are easier and cheaper than boosting the actual octane content. The first widely used fuel additives is tetraethyl lead, which substantially increased compressibility. From 1920 to 1970, particularly all gasoline sold in the United States contains additive lead, and this is basically the structure. But the increased performance and reduced fuel costs came with a price. Lead is toxic, and most of the lead introduced in gasoline will ultimately emit into atmosphere and settle in soil and water. The final blow to lead gas came with the introduction of catalytic converters in 1970. As you may know, the catalytic converter is designed to reduce the emission of carbon monoxide and other pollutants. The important chemistry of converter takes place on the platinum metal surface. The microscopic lead particles in the exhaust stream position the platinum surface by binding to it so strongly that the catalytic reaction cannot take place. Unleaded gas was introduced and gradually took over the market since 1966. It has been illegal to sell gasoline containing lead additives for use as motor vehicle in the United States. Other additives have stepped in to take on the octane boosting role formerly played by tetraethyl lead, but most widely used in the United States today is ethanol. And as we mentioned before, because adding ethanol increases the oxygen content of gasoline, it is often referred to as an oxygenate, and gasoline containing ethanol is known as oxygenate fuel. The added oxygen helps to ensure more complete combustion and therefore reduces the emission of carbon monoxide, hydrocarbons, and soot. Gasoline containing at least 2% oxygen by weight is known as reformulated gasoline or RFG, and the use of such fuel is mandatory in some areas where pollution problems are severe. Ethanol for use as fuel additives is produced from crops such as corn, barley, and wheat. Starch from these crops can be converted easily to sugar. The sugar is then fermented to produce ethanol. Because the feedstock or agricultural ethanol production does not rely on import petroleum products, gasoline containing up to 10% ethanol can be burned in any modern automobile, and mixtures containing up to 85% of ethanol can be used in designed engine. So another additive is MTBE or methyl butyl ether. It was widely used in the 1990s. Like ethanol, MTBE increases both the octane rating and the oxygen content of gasoline and fuel, with as much as 15% of MTBE can be used in any modern engine. After the passage of 1990 Clean Air Act, however, the use of MTBE increases drastically. The law mandated the use of oxygenated fuel, and the fuel industry saw MTBE offered advantage over ethanol in cost of production and transportation. However, the possible health concern over MTBE called the choice into doubt, because MTBE is a possible carcinogen, meaning that it basically can cause some form of cancer. Although the extent of MTBE impact on the human health is still somewhat uncertain, some areas in the United States actually banned MTBE in gasoline. This is basically just showing types of oxygenated fuel like gasoline, ethanol, methanol. This marks the end of our lecture today. Hopefully this was also informative. So this definitely will require that you guys practice your calculations. That's the only advice I'll have for this lecture, and I'll see you for the next lecture.